Number 9. Number 9, I've got something that looks something like this. It actually doesn't matter how carefully I draw that. It says that determine A, whether dy dt is positive or negative. Then it says dx dt is given dx dt is negative, and then determine whether dx dt is positive or negative, given dy dt is positive. Nice. All right. What the heck is that? All right. We're going to go real basic here. What does dx dt mean?
Slope.
No, it does not mean slope at all. We at this point in your calculus career, you're supposed to have an epiphany. You're supposed to read dx dt means how fast x is changing with respect to time. Time. There's no time. This is an XY graph, man. There's no time on the graph. So apparently they got some sort of little marble or BB doing something weird on this graph. It's following the little graph. And then a time thing without even an equation for time. They're just moving around. Now, that should be make your head go temporarily. Now look back there. What does dy dt mean?
The change of y over time.
With respect to time. So it tells you that's so we want to know whether that's positive or negative. Okay, so let's read the bottom one again. If dx dt is negative, what does that tell me? Which way is this little BB going?
It's going to the left.
One left. So the BB is going this way. So what is dy dt when that happens?
Going positive.
Done. And if dy dt is positive, what's the dx dt doing?
It's negative.
Negative. Good?
Mm-hmm.
Yes, ma'am.
So am I making a massive mistake by thinking about the x-axis as a time?
Yes. There's some sort of BB in time. There's like you think about it, like a little video with a little BB that's sliding back and forth. And this is its path. We don't know which way it's going. If they tell me that it's moving in the x direction of the negative, then it's going this way. So what's it doing in the y direction? It's going up. That's what's going on here. Now, I must admit, the reason why this problem's on your worksheet isn't because it's super hard to do. It's because it's that idea that you just said, which is we're so used to the dimensions being, what we're dealing with here, right? And yet they're talking about something that's not even all pictured in this thing. There's no time on this graph. If they did a YT graph, it'd look completely different. And so this is weird. This is that realm where we're playing with, hey, we just pick a random variable, we take the derivative with respect to it, and that changes what the meaning of everything the problem is. Okay? Super powerful, but also super odd compared to what we've been doing so far. Other questions? I have not done anything but the plane problem and that one. Let's do 17. Well, you hear what I told you? Don't bother with the first part.
Oh, no, we don't have to do 17.
So the first part is, what I said is this. I said, look, A is show the area of the triangle is going to 1/2 s squared sine theta. That's actually pretty easy to do if you remember any of your trig at all. And you should be able to do that. But I usually then spend 30 minutes in my calculus class showing everybody how to derive a trig expression that you're never going to use again for the rest of your life. So I thought, rather than to say do that, what is the point? Why are they asking you to do that in a calculus book, solve a random trig identity from last year? You need an equation. They're giving you an equation. So watch out for that. My whole point was watch out for that. I've written problems. There's a boat problem where I said the boat is filling with water, and I said, I said, by the way, the equation for the volume of a boat, depending on how high the boat is, and I gave a whole equation for that. Like a third of the class didn't use it. Like I wrote this random equation sitting right in the middle of the problem, and I just kept talking about the boat filling with water, and that would be dv dt, right? And it's filling in the water, and then I want to know how high the height was going, right? They didn't recognize that I gave them the dang equation like 4 lines above it. Watch out on related rate problems, random equations being suddenly inserted in the equation, right? You know, one of the other things that'll happen is they'll write this big old essay. There's one that was about what was it? It was a water tank, and it was slowly being drained by the local people as they were trying to figure out what's going on. So the water's going down in the water tank, and they gave the volume, and then this whole thing, sentence, people in Jarsville are worried about how much water is coming down the hill, all this random stuff. At the very end, it says, by the way, the volume of a sphere is, and they give you a volume of a sphere equation. Use it, right? There's a reason why they put that on there. You know, there's only about 4 or 5 equations they expect you to, like, off the top of your head, be able to pull. Pythagoras, you absolutely have to be able to pull. There's one I'm going to show you later, which is similar triangles. They expect you to be able to pull that out of your hat. That's the one you're going to not be able to pull out of your hat, so we got to talk about that. And then circles, area of a circle, perimeter of a circle, squares, and triangles. They expect you to be able to area of a triangle. Things you should probably do know. Okay. I think the similar triangle was the one that's going to get you. So just the whole point is that when you see something like that and you're doing a related rate problem, it's not because they suddenly decide that you want to know the volume of a sphere. It's because they think you need it to do the equation. And so they're giving you the equation. Yes, ma'am? Included angle. And when you're talking about a included angle, wait, what are we talking about?
Well, in the directions, it says the included angle is the 2 sides constant equal length of x.
Yeah. So
I just did
that would be this angle here.
The 2 sides of both x.
These are S and S. They can't change. And this side's changing because we're swinging the arms out. It's changing the volume of or the area of the triangle. Does that make sense? Okay. All right. Any other? Included, right? Forget it. Like, I can't find included. Questions? Ready to start the next set?
Next what?
Next set of random related rates problems that are going to cause you pain suffering.
Oh, yeah.
All right. Let's get it going. These are going to step up the interest level. That's math code for their harder.
Wait, did you do 11?
I did not. I figured I'd have to do 11 because 11's hard. How did you guys do 11? Because you didn't ask that question. I figured 11 would be, everybody would be talking about 11 right about now. So I should have paused this already. Darn it. I will do 11. 11. Here we go. Oh. 11. 11. Here we go. 11. All right. So consider the function y equals ax plus b. If x changes at a constant rate, does y change at a constant rate?
Yes.
How do you know that?
Because there's a slope which is changing.
I like it. The other way to do it, we go dy dt equals a. Oh, terrible. What the heck? This pen is not. This is my bad pen. Where's the good pen? There it is. This is a chance. Okay, so I go dy dt equals a dx dt, right? And therefore, if this is going at constant rate, then this would also go to constant rate. If I put a number like a 4 in there, 4 times a would be what the other one would be, right? But I do like the slope, constant slope thing. That was quick and better language than what I just did. Questions on any of that on 11? All right. 13. 13. I'm going to take another page here. 13. So they say the following. They say, find the rate of change between the distance between the origin, which would be the point 0, 0, and a moving point on the graph that looks like this. So I've got some sort of point on here that's moving around. And they're saying dx dt is equal to 2. So it's moving to the right at 2, right? I want to know how fast it's moving from the origin. Well, the origin, what's the equation for how far this thing is from the origin? The distance equation, which we also call Pythagoras, right? It'd be x squared, x and y. So the distance would be x squared plus y squared equals, I'm going to call it, I don't want to call it distance. What do you want to call it? Length. I'm going to call it L. C squared. C. Yeah, C squared. Well, C looks like a constant. Everybody knows that's a variable, right? Can I make it L? C squared? We're good? C squared? Are we good with that being a variable? All right. So that's got to be my equation I got to use because that's the distance between the two, right? Is this in C right there? And again, this is a hard one. This is weird because it's not what you'd expect it to be. They give you a nice equation. They give you a dx dt. Without even looking at it, you think you can do the problem without working much harder. They actually want to know the distance between the two, and that's C, right? So that's dc dt is what we're looking for. Okay? Now, if I go to do this equation, what am I going to run into? I don't know dy dt, and I don't know x and y, which is another problem altogether. Although that's interesting. Do they? Okay. So I'm going to look at this problem. I go, well, if I go to do this, I would go 2c dc dt equals 2x dx dt plus 2y dy dt. And so this is a problem right there, the dy dt, because I don't know what dy dt would be. So Mr. Welko, I can't have y in my equation. Do you have a suggestion for me?
Do substitution or something to like.
Okay, you got to find me some way to substitute y in terms of x. You got anything for me? How is y and x related in this picture?
Like the initial equation.
The original equation. This is where the initial equation comes in. I get y is equal to x squared plus 1. Agreed? I would have to put it in this ugly expression, don't I? I'd have to literally drop it right there and go, oh, please, no, really? So I would get c squared. Did I guess dx or dt, dy? Did I mess this up? Yeah, it's dx. All right, so dy all of a sudden. X squared plus, this becomes x squared plus 1 squared. That whole thing becomes squared, right? Ew. That could have been done better. C squared equals x squared plus x to the 4th plus 2x squareds plus 1. I did that fast.
Do you not want to leave it to chain one?
I could chain it. You could do that. You could absolutely do that. I like power rules, so I'm going to simplify it down to a power rule. But there's nothing wrong with what you just did. What you just said. X to the 4th plus 3x squared plus 1. This isn't going to get us much for either because we don't know what x is. They don't give us where x is at any time. Find the rate of change of the distance between the origin and the moving point on the graph, xy equals x squared plus 1, and dx dt equals 2 centimeters per second. Oh, that's very terrible. All right, let's keep going. 2c equals 4x cubed dx dt plus 6x dx dt. I don't think this is going to get any better.
Why couldn't you just plug in the derivative of x, the dx dt equals 2 at this point?
That's what I'm going to do next, yeah. I'm going to get to that. Oh, I forgot about dc dt. That's what I'm looking for. Probably should have that in the equation.